reservations in two-way slabs by means of yield lines. We will now deal with cases 31 to 35. It's about a slab which is simply supported on two opposite sides and fixed supported on the two opposite shortest sides. This will deal with case 32, which is a corner reservation. We have a rectangular slab and a two-way slab. It means that B must be between A and 2A. The reservation tip must follow the corner yield line. It means that the ratio D2 over D1 is equal as S1 over S4. And the top left corner is at 0, 0. It means that D4 and D3 are 0. And we only cut one yield line, so this reservation goes from the top up till there. So it means D1 is smaller than S4. We first deal with the case of the horizontal yield lines. It means with the limitation that alpha must be bigger than square root of 3. To visualize the reservation, then you will see that we can have a reservation going from this to there and then to this. So now you have a visual about the type of reservation we are dealing with. This is just an example. You can also take other types of reservations with other conditions, but you need to define the conditions, otherwise you cannot make a closed formula for calculating the maximum bending moment. The different values of S1, S2, S3, and S4 are, we can now calculate for the horizontal case the work done by the external forces, which is for the orange part, the rectangulars, it is the A times B minus S1 minus S3, and then multiplied by the mean deflection, which is delta over 2. For the triangles, we got A times S3 plus A times S1, but we have to subtract the reservation. Now we must be very careful because this reservation belongs to two rotation axes, this one and this one. So let's take the first rotation axis. Then it's this triangle, which is d1 times d2 divided by 2. And the maximum deflection is at that point. So this is delta times d2 divided by s1. And for the other part, rotating about this horizontal axis, it's d1 times d2 divided by 2 multiplied by delta times d1 divided by s4. And this hole has a mean deflection because of the summation of triangles of delta over 3. Substituting for S1 and S3 gives you this equation or expression. The work done by the internal forces is then yield line, this yield line projected on this axis, but the yield line is cut there. So you got, in fact, from this to this, you got B minus D2, and the angle of rotation is delta over S4. On the other side, you got B times M divided by S2, and then this is A divided by S3. This is also A projected on this axis, A divided by S3, and then we got this yield line that it's cut, so you have the length from there to there, which is A minus V1, and we got that 2 times divided by S1. Substituting for S2, 3, and 4, and S1, you have this expression. And when E is equal to D, you can find M, but we use dimensionless parameters. So we've got this expression for M horizontal. In case that alpha is smaller than square root of 3, we have the vertical pattern. Again, we know it's two-way slab. This condition applies. The yield line is at the corner and it follows the yield line. So d2 over d1 is equal to s1 over s4. Top left corner means d4 and d3 is 0. And cutting only one yield line means it goes from there to there and not passing this. There's the condition on it. We know the values of S1 to S4 for the vertical pattern. We can now calculate the work done by the external forces, which is for the green part, it's B times A minus S2, S4, and multiplied by the mean deflection of a rectangular, which is delta over 2, and that gives you this expression. For the triangles, we got B times S2 plus B times S4, but now we have to subtract the reservation. The reservation is part of two rotation axes, so for this rotation axis, we will have D2 times D1 divided by 2, multiplied by the maximum deflection there, it's delta times D2 divided by S1. And for the other portion is D2 times D1 divided by 2, multiplied by delta over D1 divided by 4. So then this total sum must be multiplied by the mean deflection, which is delta over 3. Substituting S2 to S4, we got this formula. The work done by the internal forces is equal to, for this rotation axis, we got this, when the yield line projected on this rotation axis, it is B minus D2, and the angle of rotation is delta over S4. Bottom we got B, M times B divided, of course, by S2. And on this side, we got A divided by the S3, and we got it 2 times. On the other side, we got this yield line that is cut by the reservation, so it means that we got A minus V1 divided by S1, and then we got it two times for this yield line. Substituting for S1 to S4 gives us this. Now D is equal to E, then we can get M out of it, but at the same time we will use dimensionless parameters, and then we have this expression for the M vertical. Let's give an example. We have a slab 3 by 4.8. Depth of the slab is 160 millimeters. The concrete cover 30 millimeters. Floor finish 2. The mobile load 15. What is the needed reinforcement for a slab of this type? The load in ultimate limit state is 1.35 times the permanent load plus 1.5 times the mobile load, and gives you 30.6 kilonewton per square meter. These are the different parameters. Alpha 1 is D1 over A, which is 0.33, and alpha is B over A, it's 1.6. So it means we are in the vertical yield line pattern when alpha is smaller than 1.7. And D2 over D1, you see that we have in case 32 yield line, it means of reservation, sorry, it's case 32 reservation, means that the tip of the reservation must follow the yield line, and in this case it is okay. The maximum bending moment is then with this formula 14.19 kilonewton meter per meter. To convert it into reinforcement, we calculate the mean lever arm, which is 122 millimeters, and the reinforcement is 1.1 times the maximum bending moment divided by the lever arm and the yield strength of the reinforcement. Gives you 327 square millimeters per meter, or a diameter 8 every 150 millimeters will be fine. Second example, we take an existing slab with those dimensions indicated on the figure, and we are wondering, is it okay to make a reservation in this existing slab in the corner by 0.5 by 0.85 meters? We know that or we suppose that the top and bottom reinforcement are equal, but we do not know what is the reinforcement or what was the original load where this slab was calculated for. So alpha is B over A is 1.8. So we are in the horizontal case because alpha is bigger than 1.7. The maximum bending moment without the hole is M0 horizontal divided by the ultimate limit load. We divide by the ultimate limit load because we do not know the ultimate limit load here. And then on the right-hand side, you only have an expression depending on the geometry, and it's 0.466. We can also calculate the maximum bending moment with the hole, which is M over Q. We use this expression, and it gives you 0.502 meter per meter. This means that the bearing capacity is 100 times M0 divided by M is 93. So we lose 7% in bearing capacity. So making a hole of this size in the corner, it loses you 7% of the total bearing capacity of the slab. Bearing capacity is defined at 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. In dimensionless parameters, we have an expression of this type. For a case 32 type of holes, we know that the restrictions are one two-way slab, then the size of the reservation is limited, and the reservation must follow the yield line. We have seen in previous slides that for the two different cases of alpha larger or smaller than square root of 3, we have BC vertical and BC horizontal, or you can put it into one expression. What can we do with this type of formula? Well, you can put it on the x-axis. We have alpha 1, the size of the reservation, and on the y-axis, the bearing capacity. And we can do that for different values of alpha. For red, alpha is 1, then the blue alpha is 1.5, and then the light blue is when alpha is square root of 3. That is where the vertical and the horizontal yield pattern are coming together. And the black one is for alpha equals to 2. So these are the main curves. And you can see now that almost for all reservations, most of it, the bearing capacity is lower than the original bearing capacity. Now let's look at the limit. Alpha 1 must be between those two values. We know that when alpha is bigger than square root of 3, then alpha 1 must be smaller than 0.5. And when alpha 1 smaller than square root of 3, alpha 1 must be smaller than this. Because we have two conditions. The first one was alpha 1 smaller than 0.5, and the second condition was this. So we see now in which case the condition is governing. Now we can make a small study of it. For instance, for alpha equals to 1, we look at this expression and we call EE1 equal to the bearing capacity of alpha is 1, and square root of 6 is 91.6. So this is this line, this horizontal line. This means that for the red line, the value of the bearing capacity is only valid up till this red line, because otherwise you will not fulfill this condition here. So that means that this portion of the line should not be there. This is not a valid. So it's only this that is valid. Now we can do the same for alpha equals 1.5. Then we got this limit. This is 1.5 times square root of 3 divided by 6. If you square root 3 divided by 4, I call this E2 is equal to the bearing capacity of. So you see now this is 95.9, which is the blue one, the blue curve. The blue curve. It means also now that this portion is not valid because you must always be lower than this value. And then we can do the same for the limit value, square root of 3. Of course, the square root of 3, then it is equal to, this is the blue line, of 100%. And for alpha equals 2, we have E3, which is 96.8. So for the 96.8, this is the black this limit. So we can conclude that the whole type 32, following the yield line from there to there, of a rectangular concrete slab leads to a loss of bearing capacity of maximum 10%.